The same structural mechanism that allows an enterprise AI to process natural language also acts as its primary security vulnerability. In traditional software architecture, an impenetrable wall separates the programmer's code from the text typed by the user. This illustrates the traditional safety boundary. Because these channels never interact, users cannot overwrite application code by typing into a chat box. Large language models break this rule. Because they ingest natural language, user data and system instructions travel through the exact same pipeline. The model cannot inherently tell the difference between an authorized system command given by your company and a malicious text input typed by an external attacker. Deploying an AI agent without strict technical guardrails is the operational equivalent of leaving your enterprise servers completely unlocked. By 2026, fixing this vulnerability becomes a legal requirement, as the EU AI Act takes effect as the ultimate operational gatekeeper for global businesses. This compliance chart maps AI systems into 3 distinct regulatory tiers. Any application touching consequential life decisions, like evaluating creditworthiness or sorting job resumes, falls directly into the high-risk category, triggering strict compliance rules. Operating ungoverned high-risk systems under these rules carries severe financial penalties, up to 35 million euros, or 7% of an enterprise's global annual turnover. Ultimately, securing the large language model pipeline is a non-negotiable requirement for corporate survival under modern regulatory frameworks. To diagnose the structural vulnerabilities inside that pipeline, the industry relies on the updated OWASP Top 10 framework for LLM applications. This list isolates the 3 most severe threats correctly targeting the corporate suite: prompt injection, sensitive information disclosure, and excessive agency. Prompt injection occurs when an input intentionally manipulates the language model, forcing it to override its original system instructions. A direct attack happens when a user explicitly types a jailbreak command, but the far more dangerous threat to companies is an indirect injection. Consider an agent reading external files. A competitor hides invisible white font at the bottom of an invoice. When processed via a RAG pipeline, the AI reads the hidden text and, unable to separate data from instructions, interprets it as an authorized executable command. The second risk, sensitive information disclosure, happens when models with massive context windows accidentally leak proprietary algorithms or personally identifiable information back to the end user. The third risk is excessive agency. This occurs when an autonomous agent is granted broad functionality and tool access without human oversight. Warning tone. If an agent designed solely to draft customer emails is mistakenly given direct API keys to your Salesforce CRM, a single error can permanently delete client historical data. All 3 of these risks originate from the same structural flaw: the model's inability to question the intent or origin of the data it processes. This operational blindness also drives the most frequently misunderstood risk in enterprise AI: the hallucination. AI systems do not experience illusions. They do not actively lie, and they do not reference an internal database of verified facts. A large language model is strictly a next token probability calculator. It generates responses based entirely on statistical patterns. Think of the model as a highly articulate intern. They have read millions of books and can construct perfect sentences, but they lack real-world logic.
This diagram shows what happens when you ask that system to summarize 2021 widget sales in Munich, a product your company never actually sold there. The system calculates that the most statistically pleasing response is to invent a realistic-sounding paragraph about Munich sales. It is simply fulfilling its mathematical prompt to keep writing fluid, authoritative sentences. Basic prompt engineering cannot solve this. Telling the model not to lie fails because you cannot patch a mathematical behavior with a polite request. Controlling this requires explicitly constraining the model's operational boundary using grounded RAG architectures. Under this legal mandate, you enforce a strict rule. If a fact does not exist within the approved context file, the model's only authorized output must be, "I do not possess that data." Eliminating misinformation requires bounding the model's mathematical operations with these strict constraints, rather than expecting it to magically memorize your corporate truth. To physically enforce these constraints and protect the brand, organizations must implement an independent AI gateway layer. This flowchart displays the AI gateway acting as a continuous protective firewall between your user interface and the underlying language model brain. The first validation stage is the input guardrail, acting as the inbound filter. If a prompt contains a social security number, the guardrail identifies the sensitive data and strips it before the request ever travels over the internet to the model provider. It also enforces topic restrictions, instantly blocking any attempt to steer a corporate bot into unsafe or unauthorized territories. The second validation stage is the output guardrail, serving as the outbound safety net. If the model accidentally generates an answer containing an internal API key, the guardrail intercepts and censors it before the customer ever sees it. This stage also houses the hallucination classifier, comparing the model's final answer strictly against your original RAG context files to intercept fabrications. By isolating the vulnerable model brain, this independent gateway creates the required friction to turn raw mathematical processing into a secure corporate tool. This dashboard represents a fully compliant international AI claims processing agent, demonstrating how these defenses operate in practice. The agent is tasked with reading client accident reports, cross-referencing internal coverage policies, and approving payouts under $5,000. Because this workflow touches consequential financial decisions, it falls directly into the EU AI Act's high-risk category. The first defense layer enforces the principle of least privilege. The agent is physically restricted to a single, read-only policy folder matching the claimant. This strict data isolation ensures that even if the system malfunctions, systemic sensitive information disclosure is impossible. The second defense layer relies on the AI gateway firewall to heavily scrutinize uploaded accident photos or text statements. By immediately blocking active script code hidden within those file uploads, the gateway successfully neutralizes the threat of indirect prompt injection. The final defense layer introduces a human-in-the-loop architecture to manage the agent's autonomy. To satisfy international compliance frameworks, the agent is entirely barred from executing actual financial payouts on its own. Instead, its final action is to compile the audit trail and queue a pending review ticket on a human manager screen, completely preventing excessive agency. Layered data, model, and application-level guardrails establish the structural foundation for scaling automation safely and legally in a global market.